So let's try drawing the Lewis structure for ozone. So I have 3 oxygens, each has 6 valence electrons, that's 18. So I'm going to, the only thing I really can do is line them up. I'm going to give everybody an octet. When I do that, I have 8, 16, 18, 20. So I've got too many electrons, so I need a double bond. So I'm going to redraw this. So this is the structure for ozone. Now, I could have drawn that one of 2 ways. I could have drawn it like this. Oops. Let me make them aligned so it's obvious where I've done this. I'm going to put the double bond on either side. And you could argue that this is the same, because if I just flip this, they're always rotating in space, that it's the same thing. But what you would expect then is that this is a symmetrical molecule, that the bond length here is the same, is going to be less than the bond length here. But as it turns out, that's not the case. As it turns out, data shows that the bond length for both bonds is exactly the same, and that in fact it's a symmetrical molecule. So that what that says is that this bond, this is not quite what it looks like. That what it really looks like is some hybrid of this, where this second bond is moving. It's mobile. It's delocalized. Okay. So we call these resonance structures. So here we have ozone. And we put a bracket around it and say it could be that, or this is a proper way to show resonance structures. And in fact, they are some amalgam of the two. So we use multiple structures to describe the molecule. We can't describe it with any one of those, and we put the brackets on to show that they are resonance structures. So just as green is a synthesis of blue and yellow, ozone is a synthesis of the 2 resonance structures. In fact, these bonds are identical based on all the data scientists can put together on those. Okay. Okay. So what scientists say is this second bond here that made the double is really, whoops, it's mobile. It's not localized, it's delocalized. Okay. Another popular substance, which you should know benzene. It's one of those compounds that does not go by its IUPAC name, but it's a very common structure that gets used a lot in examples. It's actually a carcinogen. We used to use it to clean out, it was a really good solvent, we used to use it to clean out dirty paint tanks. And I actually have some good friends who died from leukemia, and we suspect it's from benzene exposure. But the structure is, it's a C6H6, and if you build that, what you'll find is that we have 6 times 4 is 24, plus 6 is 30. Each of these has a hydrogen on the outside. 1, 2, 3, 4, 5, 6, and that I don't have enough electrons to give all these carbons a full octet, so what I end up needing is 3 double bonds. So it alternates double bonds. So you could argue whether it's the double bond is here or here. In fact, benzene is often written with this shortcut, and what you see when you look at the structure of benzene, scientists look at it, is it really does look like a ring structure with the electrons forming this circular pattern. So the electrons are delocalized, they move. Okay. So let's take a look. Let's predict which of these are going to have shorter sulfur-oxygen bonds. So I have SO3. Let's draw the Lewis structure. SO3, that's 6 from sulfur plus 3 times 6 from oxygen. That's going to be 18 plus 6 is 24. So I have SOO. I'll do it like this. And give everybody an octet. If I do that, I have 8, 16, 24, 26. I have too many, so I'm going to make a multiple bond. And if I do that, then I really need to draw 3 structures because this is a resonance, right? And the double bond could be on any of those. Oops, that one's not there. Let me use my eraser and erase that. I'm gonna move to my lines because I am really sloppy, as you can tell. Okay, so this is SO3, right? It's a resonance structure. Now let's for SO3 minus 2. So it's going to be the same electron count plus 2 electrons. So if I do that, that was the original structure I had when I had full octet everywhere, right? And I have 8, 16, 24, 26. So I don't need multiple bonds here. And this is a minus 2. So here's the deal. So which has shorter bonds? So if I have a single, a double, and a triple bond, the triple bond is going to pull those atoms the closest together because I have greater electron density pulling on that. If I have a double bond, it's going to, I'm doing this wrong. If I have a single bond, it's going to be like that. Double bond is going to move them in closer. Triple bond, really high electron density between them is going to move them really close. So the more electron density in between the 2 nuclei, the closer those bonds are going to be, the atoms are going to be pulled. So the bond length gets shorter as I add a multiple bond. So here I have all single bonds. Here I have singles and doubles. So remember, these 3 bonds are really sort of an amalgam of the 3. So it's good. The bond length is going to be a little longer than the single bond, but a little shorter than the double bond. So the shortest bond length is going to be my SO3 because I have no multiple bonds here. Alright, so let's draw 2 equivalent structures for the formate ion. So I have carbon, so at least the electronegative is going to be in the center, O and O, C, O, O, H. And I have 1 electron, 4 electrons, 6 electrons, and this is 1 electron. So this is 12 electrons. So I have 2, 4, 6, 8, 10, 12, 14, whoops. Let me see. Whoops. This is my problem. I have 6 plus 6 is 12, so that's going to be 18. Alright, that's 12 plus 4, yeah, 18. So I have 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. Okay, so I need a double bond, and I'm going to take them away from there and put them here. I'm also going to do the same thing over here, because this is resonance, right? And then I put my lone pairs to give everybody a full octet, and that should do it. Okay, these are resonance, so I put them in brackets.